The next speaker is Hirotaka Hayashi, and he's talking about UN spectral covers from Decomposition.
Thank you. First of all, let me thank the organizer for giving me a special opportunity of having a talk in this very nice conference. So today I'm going to talk about the UN spectral covers, which I obtained from the Decomposition spectral cover. And this work is in collaboration with Kanshin Che. And let me start from the motivation. And the candidate for beyond the standard model, minimal supersymmetric standard model has been studied extensively so far, and this MSSM can predict grand unified theory in a very high energy. And in a simply simplified grand unified models, standard model matter content here are summarized in a nice representation of SU5 grand unified gauge group. And if we write down generic superpotential, we have necessary interactions here, but from the gauge invariance only, we also have to have this kind of coupling, which leads to a rapid proton decay. So typically, we want to impose some symmetry, like a U1 symmetry or discrete symmetry, to forbid this kind of coupling. And if we consider a string computation to realize a standard MSSM or a grand unified theory, we have to find how we realize this kind of U1 symmetry or discrete symmetry from string complications. So today I'm going to focus on F-theory complication and tell us how we can realize this U1 symmetry from S-theory complications. So in fact, but in F-theory complication, U1 symmetry requires a global analysis, and the number of U1 symmetry are counted by this kind of formula. And if we have non-abelian gauge symmetry in low energy effective field theory in 4 dimensions, we have some non-abelian singularity in Calabi-Yau 4-4. So we usually resolve Calabi-Yau 4-4 to count this H1, and the number will become a rank of the non-abelian gauge group. But we want to further engineer U1 symmetry, which is not associated with non-abelian singularity. So we have to find some tunings which increase this H1 by 1. To have another U1 symmetry, which can use to forbid from dangerous operators in low energy effective field theory. But it is in general difficult to find this kind of parameterization from purely F-theory point of view. But so we use the heterotic F-theory duality to find this kind of tuning. So we first use spectral cover construction heterotic string theory to find these parameterizations. And actually there are other solutions proposed by those people, and actually our parameterization contains one which are not equivalent to those ones. So first we start from the heterotic string theory. So we consider heterotic string theory on the background of Calabi-Yau 3-4 with a vector bundle on it. Then we achieve an n=1 4-dimensional supersymmetric field theory with some gauge group G, which is a commutant of E8. And if we further require this Calabi-Yau 3-4 has an elliptic vibration, then we have a nice construction of stable SUN vector bundle using a spectral cover formalism. So if we consider SU5, if we want to consider SU5 gauge group, then we turn on some SU5 vector bundle. Then we need a 5-fold cover, which is a cover over this space manifold, and this 5-fold cover intersects this elliptic vibration with 5 points. And in order to ensure this speciality of unitary groups, then the group sum of these 5 points should correspond to a zero section of elliptic vibration. Then if we want to engineer a U1 symmetry in a low energy effective field theory, then we can consider a vector bundle full structure group which is also decomposed in this way. Then this vector bundle can be associated with a spectral cover, which also decomposed into 1-fold cover and 4-fold cover. And this 1-fold cover intersects with elliptic vibration at some point, but this Q1 does not correspond to a zero section. And this sum of 4 points, which are intersection points between this 4-fold cover and elliptic vibration, the sum of these 4 points also does not correspond to a zero section. But sum of all these 5 points should correspond to zero section to ensure the speciality of those unitary groups. However, so this kind of spectral cover can be constructed if we find some equation which describes this 1-fold cover. But actually, this is impossible since there are no elliptic function which has only 1, 0. But actually, if we tune the compressed structure modular curvature threefold to have another section which is different from zero section, then we can associate this one-fold curve with this another section. Then we can actually construct this decomposed spectral curve. So, so let me move on to one example. Then, this is the elliptic fiber curvature threefold equation, and this SU5 vector bundle can be characterized by this fivefold curve spectral curve equation. And so local factorization of the spectral curve can be understood from the decomposition of fixed bundle ansatz, which are considered in F-series computation originally. And so that 1+4 factorization in F-series computation requires this kind of parameterization for the coefficient of this spectral curve equation. And actually, so if we use this kind of parameterization, then this point Q1 x and y is equal to b0 squared over b1 squared and minus b0 q over b1 q is on the spectral curve. So we can require this point to be a global section in elliptic fibration. Then, so if we require this Q1 to be a global section of elliptic fibration, then so this Q1 should be a solution with elliptic fibration regardless of f and g. Then we have a relation like this to make this Q1 to be a global section, and this equation can be parameterized in this solution. Then, so to ensure this gives really a global section, then we can rewrite the elliptic fiber equation, which I showed before for elliptic fiber threefold. Then that equation can be written in this way. So from this equation, we can clearly see that there is a global section which comes from this part, this component, this component. So like this, we can construct the 1+4 factorized spectral curves, and also in a similar logic, we also constructed a 2+3 factorization and 1+1+3 factorizations. Now, so this is how we construct the factorized spectral curves in heterotic string theory, and we can also interpret this result from F-series complications. So the duality of heterotic F-series duality is summarized in this way. So heterotic string theorem elliptic curvature threefold with a vector bundle is dual to some F theorem elliptic K3 5 curvature fourfold with some base S and in the stable degeneration limit. So stable degeneration limit means this K3 fibration is decomposed into two rational elliptic surfaces which shares a common elliptic curve. So now we want to count this number in our parameterization we found. Then these two forms can be characterized by the two form which has one leg on elliptic fiber and the other leg on base threefold. And this is Poincare duality monodromy invariant two cycle over the base. I mean monodromy invariant two cycle means so there are some two cycle which are some two cycle in the rational elliptic surface. Then we go around some point. Then there can be a monodromy which exchange with these two cycles. So then this does not correspond to global 6 cycle. So this does not correspond to the element here. So we have to find how many monodromy invariant two cycle which remained in our parameterization, and this ensures if this if we found this monodromy invariant two cycle, then we can say that there is an U1 symmetry corresponds to this component. So okay, thanks. So you have to study monodromy two cycles, then we can see the monodromy of the location of membrane. Then location of membrane can be studied by considering a discriminant of Tate form. So we consider a K35 curvature fourfold with an A4 singularity in the stable deviation limit, and that can be written in this way. And so this equation has an A4 singularity, and actually there is a very nice map between heterotic string theory and F theory. So actually those parameters which I denote A0 and A5 are actually the bundle moduli and the same parameters which appeared in the spectral curve equation, and this F and G are also compressed structure moduli of heterotic string theory. So the location of membrane are just a discriminant of this curvature fourfold, so we can easily compute the discriminant here, and this D25 represents a 5 membrane for realizing AC5 gauge symmetry, and actually there are other component which is a degree same polynomial in Z. So this degree same polynomial represents the location at the same branes, but those same branes are mixed by monodromies. So in order to see whether the monodromy of same brane is reduced or not, we further see the discriminant of this degree same polynomial. So we are going to focus on the discriminant of Calabi-Yau equation. And actually the discriminant is really complicated and I can't write in one slide, so I just write it in a very schematic way. And the discriminant of discriminant can be written in this way, and those A and B, large A and B, are very complicated function of the AR, which are AR and F and G, which are complex structure moduli of Calabi-Yau, and in other words, those AR are the bundle moduli and this FG are complex structure moduli of Calabi-Yau in heterotic string theory. And actually, miraculously, if we apply the parameterization we found from the heterotic string theory, this very, very complicated function will be factorized in this way, which includes a quadratic form. And the monodromy is locally always D2 monodromy. So this quadratic term may imply the reduction monodromy. In fact, we also checked explicitly the toy model, which is a E6 gauge series of 1 plus 2 factorization. Then we can, if we apply the parameterization we found, we actually explicitly see the reduction monodromy from S3 to Z2. So, so this in this computation, actually it is the monodromy coming from the quadratic component is trivial. So this explicit computation also implies that this appearance of a quadratic component is very essential to reducing monodromy. So we expect this SU5 case also the monodromy is indeed reduced, which is also expected from heterotic string theory. So let me summarize. So here we explicitly construct spectral covers of vector bundles whose structure group is S of U1 times U4, and actually in our paper we also constructed this 2 plus 3 factorization and 1 plus 3 factorization spectral covers. And in order to construct this spectral covers, it is very important to change the complex structure modular Calabi-Yau to another section, because we associate one fold cover to the another section. And in F-theory computation, if we use this parameterization, then the discriminant of defining equation gives a quadratic component, which may indeed imply the reduction monodromy. And actually, we explicitly check this reduction monodromy in the special case, which is the E6 gauge symmetry of 1 plus 2 factorization, 1 plus 2 decomposition. Thank you.
Thank you very much. Any questions? Huh?
I have a question on the heterotic side.
Yes.
So let me assume that I have an elliptically fibered threefold with one section.
You mean zero section? One section, zero section?
Only one global section. So a single global section. Now it is
so
generically.
if you write down Weierstrass equation, then there is always a zero section. So what do you mean?
I just mean the zero section.
Okay, yeah.
So let's assume that we have that, and let's say I have an indecomposable SUN bundle that I tune in its moduli space so that it decomposes. That's generically possible just in the moduli space of stable SUN bundles. You can do that. Would you say in the case that I have only this one section, not the extra one, that in that case, if I were to break this bundle and I can't describe it as a spectral cover, would you say that you don't have a heterotic, an F-theory dual to that heterotic theory, or that the spectral cover should have vertical components?
So you mean, even if we do not change the compensation modular Calabi-Yau, then?
Yeah. So you can certainly do that for bundles that aren't described as spectral covers. But then my question is, so sort of what breaks down in the duality that at this point? Is it just that I don't know how to write down the F-theory dual, or that I would write down a spectral cover, but it had to be degenerate in some way?
But
You suggested you discuss it in private? Yes.
Thanks.
Any other questions? Okay, well, so let's thank again.